calculation is validated against a published experiment, and the results are also compared to the ACI 4401R15 code. The results show that the rupture modes predicted in the analytical study were comparable to those of the experiment, and the average ratio of flexural capacity calculated using nonlinear stress strain to the experiment ranged from 0.78 to 0.86. Furthermore, flexural capacity obtained using a nonlinear stress strain curve for specimen with reinforcement ratio higher than the balanced reinforcement ratio performed better than that obtained using the ACI code. Next to introduction. Nowadays, steel bars are the sole solution to reinforced concrete structure in Indonesia. On the other hand, an aggressive environment would shorten the surface life of the reinforced concrete structure since chloride ion and CO2 result from the carbonation of concrete would corrode reinforcement bars. Corroded steel bars initiate cracking, failing the concrete cover and cause of the loss of usability. FRP bars. Demand for the use of fiber-reinforced polymer or FRP bars in place of steel bars ascended when the market needs for non-porous reinforcing bars have been growing since the late 1980s. FRP bar is preferable because it has beneficial characteristics such as high tensile strength, lightweight, and corrosion resistance. So, the purpose of this research is to investigate an analytical procedure for calculating the flexural capacity of beam reinforced with glass fiber reinforced polymer bars. Next to method of analysis. The first is description of specimen. The specimen analysis in this study are taken from a published paper. Two series of simply support beam, namely FB and HFB, were constructed and tested under monotonic loading. All specimens were identical and had a span of 3000 mm to maintain the ratio of shear span, or A, to effective depth of 3.4. This is a table. This table is present details of specimen analysis in this study. Next to material characteristics. Based on target concrete strength, the beams were split into two groups. The concrete strength of FB specimen was 34 MPa, and the concrete strength of HFB specimen was 45 MPa. And all beams were reinforced with GFRP bars with a nominal diameter 12.7 mm. Next to Flexworks strength calculation procedure. The first method is Todeschini nonlinear concrete curve. The procedure to calculate the flexural capacity of reinforced concrete beams reinforced with GFRP bars proposed in this study is developed based on the strain compatibility and internal forces equilibrium. The analytical procedure is begun by assuming the location of neutral axis or C of the reinforced concrete beam as seen in figure 1. The section and material properties for both concrete and the GFRP bars are the first input, and then both strain at the concrete and GFRP bars as seen in figure 2 are calculated based on the assumed neutral axis location. Later, the compressive force at concrete or CC and the tensile force at GFRP can be determined based on respective strain of the concrete and the GFRP bars. The assumed neutral axis applies if it satisfies the equilibrium of the internal force in the concrete section. Compressive force at concrete can be calculated using equation 1. This is equation 1 where Cc is the concrete force and K1 is the ratio of average stress to the maximum stress. F accent C is the concrete strength, and C is the location of neutral axis, and BW is the width of the beam. And equation 2, Mn is the flexural capacity, and Z1 is the distance from the concrete force to the neutral axis, and Z2 is distance from the tensile force of F FRP to the location of neutral axis. This is a stress-stress distribution in reinforced section according to Todeschini nonlinear concrete curve. In A is concrete section, B strain distribution, and C is stress in concrete and FRP bars. The next method is equivalent rectangular concrete stress block. And this is equation 3, where AF is depth equivalent stress block, and AF is the area of FRP bars, and FF is the stress in FRP bars under tension, and F accent C is the concrete strength, and BW is the width of the beam. This is a stress-stress distribution in reinforced concrete section according to ACI 4401R15. This is equation 4. Beta 1 is the factor that depends on the concrete strength, and epsilon Cu is the ultimate strain in the concrete, and epsilon Pu is the rupture strain of the FRP reinforcement. This is equation 5, 6, and 7. Next, the result and discussion. The first is rupture mode. This is a table 2. Table 2 compares the rupture modes in the experiment and the rupture modes that result in the analytical study. Failure of beams in the experiment occur in two modes: specimen FB2, FB3, FB4, HFB3, and HFB4. The rest of the beam experience failure in the form of concrete crushing, where cracks were observed in the constant moment region. Rupture modes in this analytical study are defined by comparing the ratio of FRP bars, the balance ratio. So, table 2 shows that the rupture modes in the analytical study are comparable to those of the experiment except for the HFB6 beam, where the specimen failed by bond failure. Next to flexural capacity. The comparison of the flexural capacity of beams gained in the experiment, analytical calculation using Todeschini concrete curve, and ACI code is presented in table 3. This is a table 3. Overall, the flexural capacity predict using Todeschini concrete curve underestimate the flexural capacity gain in the experiment. This is a figure 4, shows that the average ratio of flexural capacity calculated using Todeschini curve to those of the experiment for the FB series specimen is 0.76, and the standard deviation is 6%. And on the other hand, and seen in figure 5, this is a figure 5, the average ratio of the flexural capacity of Todeschini curve to those of experiment for the HFP series beam test is 0.86 with the standard deviation of 7%. Furthermore, for the specimen with reinforced ratio higher than the balanced reinforcement ratio, FB6, FBH, HFB6, HFB10, flexural capacity calculated per Todeschini curve result better compared to those of ACI code. In this case, compression concrete reached the ultimate strain epsilon Cu equal to 0.003, while the strain in the FRP bars is lower than its ultimate strain. The stress-strain concrete curve is fully formed, and causing the contribution of concrete force to the flexural capacity of the beam section is maximum. Next to conclusion. So in this study, an analytical procedure to predict the flexural capacity of beam reinforced with GFRP bars was conducted. A nonlinear stress-strain relationship was used to examine the contribution of concrete under anaxial compression. The flexural capacity obtained in the analytical study was compared to the result of an experiment published in the literature and to the result calculated using the ACI 4401R15 code. The result demonstrated that the rupture modes predicted by the analytical study were comparable to the rupture modes observed in the experiment. Furthermore, flexural capacity gained with a nonlinear stress-strain curve for the specimen with reinforcement ratio higher than the balanced reinforcement ratio result better compared to that of ACI code. This is a reference in the study. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you for your excellent presentation, Dhea. Okay, let's next presentation. Please welcome our fifth presenter is Prof.